Another application of dynamic programming we can see is in finding the optimal binary search tree. So binary search tree is a tree which helps us in searching items in a more efficient way, and the efficiency of this searching depends on how well the tree is organized. So one of the most common applications of optimal binary search tree is found in designing a compiler. A compiler is one which converts high level language into machine level language, or say a .c program into .exe code. So in doing this, so it has to be language dependent, and when you're talking about language, every language will have some special words called the keywords. So the first priority of any compiler is to identify these keywords and then look for their structure, and is there is any flaw in the structure of this arrangement of the keywords, then we raise an alarm, and which is what we call syntax error. Done. So every language will have some special words called keywords, and these keywords have specific meaning. An example in C, you can say keywords like for, while, if, then, else, and all. So many are available. Now the question is, when we read the text, which is called a program. Yes, for us it is a program, but for a machine it's simply a sequence of characters, blanks, new lines, and some special characters, punctuation marks, and so on. So from this heap of text, the machine without any intelligence must be able to identify the meaning of the program. So the first step is to search for the keywords in this text, and then once the keywords are found, then attached to every keyword there are some rules, and that's what goes the next one. So check with the rules, and if there are any flaws in the rules, any flaw in the text, it's not following any rule, then raise a syntax error. So that's a very common practice while building a compiler for any language. Yeah, the next step is to identify whether a word in the text, whatever we find, is a keyword or not. So for that, what you need to do is to have a list of keywords. Okay, then every word compare with this list, every word compare with this list, and if the word matches with any of these, then declare that a keyword is found, and every keyword is given with a code. Every keyword is given with a code, and our first step of the compiler has to identify keywords and replace each keyword with its appropriate code. And the second step is look with these codes and try to correlate the codes and see everything is intact. If no, then raise syntax error. Done. So we work with a set of keywords, and this set is usually a big one. And searching every word in this big list is highly time consuming. So every word we found in the text of this so-called program file, every word has to look into this keyword list and see whether this word matches with any of these keywords. If so, return the code. If not, then just neglect, continue to the next word. That means there may be m words in this, and there can be n keywords here. So for every word here, a keyword has to be verified. So it's something to order of mn, which we can say order of, say, n square. It's a little costly affair because n is big size, m is also big one. Therefore, it is highly time consuming. So some way we need to find out to speed up this process. But how? Yes, this list of keywords arrange most efficient way so that the time required to search is least. Okay, so what's the problem? The problem is one, that the list of keywords is large. Second thing is the probability of each keyword being used is different for each keyword. So if you look at them, you can see if then else, if then is most commonly used. Next commonly used is for. Then in some cases else also comes into picture, but as a early programmer, while loop is almost rarely used. But if you are one who is working with programming for a long, yes, you do prefer to use while loops in many cases, but whatever, the probability of using each one is going to be different. So the next issue is this list, how do you want to present it? So of course it has to be better presented in the form of a tree and helpful in searching. Therefore it has to be a search tree. Search tree means a node here, a node here. So usually we prefer binary. Done. So binary search tree. So something log n we expect from this. Yeah, the depth of that is log n. Fine. But the issue here is if you are looking for this, you get the answer in one search. If you are looking for this, then it has to have two search. One here, it says no higher than that, then it comes here. Yes, it is. So this needs one search, this needs two search, same way this needs three search. As you go deeper and deeper, the number of searches will keep increasing. So that's one issue. Second issue is the probability of each keyword is different for every keyword. Therefore, efficient way of presentation would look like the root should be occupied by the keyword which has got a highest probability of being used. So a large number of times this is used, therefore in one step you get the answer, and the deep down you can use the one which is least probable of being used. So in this way what happens is, to reach this point we may take multiple steps, but this is taken very few number of times, and therefore this doesn't make much difference to our search time, and that's the main logic behind building this optimal binary search tree. So what we need to do is one, work with the probabilities being used for each keyword. Now the question is, are there only keywords in your program? Definitely no. So your program will contain keywords and then what you call the name of the variables and many more such things. So if you just look into a dictionary, yeah, because search tree, when you say you are talking about a sorted one, sorted means I am looking at some dictionary. Now if you look at the dictionary, these words are very small in size compared to the number of words the dictionary includes. So there may be for here, and if maybe here, then who will come next? For will come. If in between we missed else, okay, else comes here, then may come here, while may come here, and so on. So in between there are so many possible words, and whether they are used or not, it's immaterial, but these are possible to be used as variable names, or any other combinations are possible. Now at the end, what is important is, so we have two sets. One set is called set of your keywords, and other one set of other words used in your code. So using these two, we need to identify the pattern of the tree, pattern of the binary search tree, such that the overall search for any item can be made possible with the least amount of time. That's the aim of working with or designing an optimal binary search tree. So that's a intro. I can talk about why binary search tree is required and where they can find their applications. So just one application was in compiler, but everywhere where the actual size of the dictionary is very big and in reality the number of items you are using is finite, then every such place, of course, a binary search tree comes to our aid and makes our life more easier by making the fastest results possible. How all these things work? So we continue looking at some numericals and then try to build the trees and then verify which tree makes the best possible thing. And yes, we can think of building all forms of trees. That's a brute force method, and that's going to make anybody go wild. Definitely not, nothing like brute force is tolerated. So we need to do it a systematic way. And one systematic way is do it in smaller chunks. Start with a smaller problem, then with time increase the size of the problem, and with that finally reach the total goal. So sequence of problems are used to solve, and that's the basis of dynamic programming. So let's apply dynamic programming to solve this problem and see how it can be helpful to us and how it makes our lives very, very simple and more comfortable. So keep watching. Thank you.